I'm very excited about this meeting, and I'm very grateful that I have been invited here. I'm going to talk about knowledge generating machine learning, interpretable machine learning, and about several areas of understanding, and you will soon see also several layers of misunderstanding. The usual problems I won't go into. You know, we have our opinions about God's representatives of Earth, people from machine learning, AI people that in the beginning still have not taught the ordinary AI users to get good data. Experts do it fantastically well in machine learning, and a lot of people think it is easy, and then they don't get enough informative data, and they didn't do it anyway. Good enough validation in the old days. There was a lack of culture, maybe, for combining knowledge and data in the AI community, and now it's better. And based on what I call the informative converse paradox, there's prior knowledge. Using prior knowledge can stop you from making new correct discoveries, because you become colorblind by the things that you already think is true. And then there is this black box aspect. But I won't talk about all those things. I'll talk about 4 subjects. The problem of subjectivity, because what I want, I've been in this game for 50 years now, or 52 years. For the first 20 years, I worked very actively against those who wanted to do mechanistic modeling. I was PA and eventually a PLS person, empirically. And I hated people who claimed things that I could see from experience that is not true. But then it looked very nicely because it looked causal. Like, for instance, if you have a lot of specular reflectance in NIR, spectroscopy, reflectance or transmission, and you take log 1 over reflectance, do PCA, you will get a couple of components which are just have peaks and valleys in the loadings, which are just picking up nonlinearities because of the specular. But people then in conferences start discussing that wavelength means this molecular vibration and that molecular vibration. Oh no, this is jumping to a conclusion. This is theology. But then for the last, was it 50 minus 20 is 30 years, I've been trying to push us towards interpretation, but not to put the carriage before the horse. But we want the carriage and we want the horse. Totality and interpretation. So, subjectivity and then sloppiness. Subjectivity is that the chosen model may be wrong. Sloppiness means that the parameter estimates from fitting a mechanistic model to data may be wrong. The pair problem is, I'll show you, stretching the data too hard may be very painful and cause a lot of damage to your mental models. And the banana problem is that the bilinear subspace may be too efficient. The bilinear, especially in PLS, is almost too good to be useful. And you wouldn't expect me to say that, would you? Anyway, so here's an example. I almost vomit when I see this data, and my friends have seen it so many times. But it's my last day in the lab 20 years ago. But it's a set of calibration and test data on a binary mixture of protein and starch. And submitting this to PLS regression, we had 5 mixtures. We had 3 mixtures that we used for calibration. And you can see the PLS does a reasonable job, like maybe some nonlinearity, but a reasonable job. And when we got the prediction test samples, they seem to do a good job of interpolation. And we could even get the regression coefficients. But it would be deadly dangerous to start interpreting that and that, because the regression coefficients are only telling how the data are being used. It does not tell you about causality. But a lot of people think that they can interpret that. If you do enough nonlinearity, horrible things with with specular reflectance. You get a lot of peaks here, and they are totally meaningless. It's just that they correct for nonlinearities. And the PLSR, this is most of the explainable AI end up at this level. And Tom Fern showed that in a very nicely way. He looked at the sensitivity of the AI solution, and you got an interpretation almost like a regression coefficient. A lot of statistics do the same. And you could even jackknife and get an uncertainty, for instance. But the special about the subspace analysis of geometrics is that we can walk inside the subspace of the data and look around and see what is going on here. We can understand. Here can we understand, the validation says we can understand that it works. Very important with validation. Here we can understand how it works. Also very important, very nice, but it doesn't give you causality inside. It just can reveal horrible mistakes. Here we start understanding why it works. That is where the chemists differ from the AI or the statistician. Not everybody is statistician, but for many statisticians. We don't know the domain. And here in this case, we have 1, 2, 3, 4, 5 mixtures. And each of these powders have been pressed together to different degrees before we measured them. So we changed the light scatter, the effective optical path length. And lo and behold, they, for each of them, form a straight line. And they meet at that point. And this point is up that line. And what is that? Well, that is, I think, the absorptivity or the absorbance that you would get if you had infinitely short path length, optical path length. In fact, you had no sample present. And if you subtract that from your original data, you just subtract that flat baseline. But what happens then is that you go from centigrade or Fahrenheit to degrees Kelvin. You go from what a statistician would call a linear model to what the mathematicians would call a linear model. Namely, 0 means 0. And once you have done that, everything else, the physics of the data, then come at you in a completely different, simplified manner compared to having to deal with this offset on top of everything else. You can also see that they are not equally spaced. That's magic. They are not equally spaced. Why is that? I mean, this is just, Beer's law said they should be equally spaced. So these are the pure powders. They should lie on a straight line, but they are on a curved line. What is this? Well, it is Beer-Lambert's law, where you have a linear relationship between the absorption, chemical absorption, and the concentration of the components, and a linear relationships also with the light scale, the effective optical path length, because the protein powder and the starch powder have very different light scattering. And so you get the product of light scattering and light absorbance, so you get a second degree polynomial all of a sudden. And for 35, 40 years, I thought I was looking for linear relationships. I hated second degree polynomials because I felt that that was just something that people were doing. Anyway, so when we use the insight that we got from here, we could design this optimized EMSE treatment. And then we can select, we can change those data so they look like this. What you will see here is now all of a sudden the same data give a much better predictive ability. And we have indications now that translectance data behave the same way. I don't think reflectance data will behave as well as this transmission data of powders, but they will be pretty close, I think. So we are in that process. So now, knowledge-based and knowledge-generating machine learning. We have a project, we have a start and a purpose, and make a plan, we have big data. We have some limited understanding, for instance, about constituent spectra, mathematical models of mechanisms, maybe differential equations, then we know something about noise levels, then what? So here's one way to do it, knowledge-based and knowledge-generating ML. So we start out by, for instance, a pre-processing of the optimized MSE, or maybe the ordinary MSE, or some kind of pre-processing, which is deductive. We have a theory, and we think that we can apply a mechanistic model to quantify the knowns. And then we spit out those knowns, quantify those as latent variables, and we get what is left. Then we do an inductive part, a machine learning, a data-driven part, where we use some kind of subspace modeling first to discover and quantify the unknowns. That's the PCA, PLS, and these things. And then we sweep the floor with a neural net to see if there is something else that didn't fit into this subspace. The point here that this is so low dimensional that we can interpret it. So that means that when we have shaved off all the things that are known and unknown but very obvious, then the neural net will probably find very few things, if anything. But it could be very, very important. And so then there should only be random noise left here. So that can be summarized and thrown away. And now we have three types of outputs. And now we have the very important third stage, an abductive stage where we model, display, and integrate the different outputs and go get a holistic model and use it for all kinds of purposes. And then we are back a new cycle we have solved the problem engineering-wise, but we have also gained new insights so that next day part of what we have learned here has become part of the not so limited understanding. So now, subjectivity. The choice of mathematical form, model form, is the most subjective part of science. Some of you don't like that. Achim and I had a quarrel about that on the plane, because I'm sure he's right that I'm wrong in the sense of infrared spectroscopy and from first principle models. I'm not saying it is wrong, but it's certainly not complete. So for instance, here we have the same data. We got non-linear data first, and then we linearize it. This was, oops. Yeah, but so the subjectivity, I had a student where we said, how can we find the ways, how are the ways in which we can deviate from a straight line for all kinds of connecting data and so on. So we found 40 different models that gave different deviations in a simple univariate XY plot. And we simulated the shit out of each of them and got 50,000 curves, did a PCA of those curves with lot of different models from different walks of life. You see some of them here is the logistic curve with different parameter combinations. Did a PCA, found that 99.3% of the variance in all these 50,000 curves could be described by the 6 principal components, which had scores and loadings. And so every new curve from any of these 40 models could be projected on a 6-dimensional subspace, in a microsecond. And so we could thereby, for each new curve, we could see what else, which of these models could be suitable. Process 2, Gutenkunst. Some of you know the famous paper of Gutenkunst from 2007, that all biological differential equation models, mechanistic models, are mathematically sloppy. That means many different parameter combinations can give the same fit to your data. So this is the case here that we had 2 different representations, 2 different models. That's just one beginning. But when we look at the law of mass action, which is the only natural law that has ever been discovered by Norwegian, my country, we are very proud of that. And we hope that it is not sloppy. We don't like that. So we take the simplest version where you have the reaction rates of formation and depletion, and then you have the reaction order, and this X is the concentration, and it is the dynamics. And we make, for instance, one model with a certain parameter combination of A and alpha, beta, G, and H. And then we have 256 starting combinations to span this four-dimensional space to find how to make simulations, and we then use simplex optimization to find these parameters to fit this data. And then we found that 84 different parameter combinations fitted equally well to the data. And then when we did a PCA, we saw that it was a typical two-dimensional solution, and we found the true value that we had simulated with is here, but all these other 48 parameter combinations gave the same fit. So there's a manifold in a very low dimensional space. It's called the neutral parameter space set that give exactly the same performance. So if we had simulated with this, or with this, or with this, or with this, it will look the same. If we had then used just simplex optimization and fitted a nonlinear dynamic curve to our empirical data, then some people would claim that this is what God has given us, and some people say that that is what God has given us, and some people will say that no, this is what God has given us, because this is what like the causal model would give. It just depends on the starting value. But there is a structure, and once the mathematicians saw this, they could greatly simplify the mechanistic models, because then, but I don't have time to go into that. My point is that sloppiness is a very important aspect of mechanistic modeling, and we should be aware of it. Just because you get some solution doesn't mean that that is what reality uses. So, yep, the only law of nature discovered by Norwegian is sloppy. We hate that. So the third problem is, you have something, you see appear, I see a square, because I want to have a straight line. But linearizing something has stretching the data so that you get a straight line, has a price, you pay a price. Because you have a tacit mental framework inside which your concepts lie. What is it, the units that you are modeling inside? And that framework, you screw that framework also. This has to do with life as well, but it certainly has to do with what you do in the lab. There is a cost involved in going either way. And in order to be honest, you have to look at the consequences outside your own little focus in whatever you do. So, then we come to the banana problem, which is, I think, the last, I hope. The bilinear subspace model, especially in PLS, is far too efficient if you want to look for causality. Because by crossing two straight lines, you can very much approximate a curve. So you can get away with linear models or bilinear models, you can get away with a lot of different models that seem to be true, causally true, just because you are using a far too efficient mechanism. And this is how it comes about. You have a, let's say, a three-dimensional, could be a wire here, and then two X variables, a banana-shaped cloud line in a very high-dimensional space. So what you do is to put a knitting needle, a first principal component, so PLS component through the length of the banana, the second one on the curvature, and you're happy. It works. Put a plane, you have caught 95% of the variance in that banana, and you can then make fantastic predictions. So you have made a boomerang out of the banana, a linear model of a highly curved structure. And there are a million ways in which you can, nature or your own mistakes, generate deviation from a straight line. And all of them, many of them, will end up as nicely looking linear models. Please, yes? This must be reality itself. So for instance, the PLS regression uses a linear structure model, but can often handle nonlinear responses automatically. And it looks like it is finding reality itself when you open up. As I said, the strength of PLS is that you can walk inside the data space and look around and say, hey, now I can start understanding why, not only how, but also why my model works. So, for instance, vector reflectance, as I said, and almost saturation and absorbance peaks, that is result, is handled this way. I'm very soon with it. For the last, I'm 77, I've never worked so hard, honestly, in my life as for the last half year with understanding this. I call it Tyrannosaurus Rex modeling, or transmission and reflectance explained. So when you have analytes that differ both in chemical absorption and physical light scattering, then you get a second degree polynomial, not a first degree that I thought I was for 30 years expecting. So the banana analysis, how many A's is that? Banana analysis can make wrong mechanistic models look right. So I'm in favor of trying to develop mechanistic models, but I'm very much against arrogance in that process. Just like I'm very much against arrogance in the machine learning. And I hate the little arrogant voice in the back of my own mind, because we all want to be right. So John Tukey was my first encounter with statistics in many ways from Bell Labs, who refused in the end to be a statistician. He just wanted to be a data analyst, but he was a fantastic person. He said that he quoted somebody else again who said, it is better to be approximately right than precisely wrong. We need a kind of a chemometrician's linear algebra, semi-coordinate modeling. That's what you talked about how we strive to understand, but we are not saying, yes, now we have it. This is so simple. We need big data where the multi-channel measurements are being combined with space and time. And we now need knowledge-based, but open-ended and knowledge-generating machine learning. Traditional mechanistic model is very good at that and very closed, very bad at knowledge generating. And the hypothetic deductive method is such a costly and a slow process. It works. We have sent people to the moon that way, but it's a tedious process. We can make it much more efficient than that when we have multivariate analysis. Thank you.
How cool was that? Are you sure you're retired?
So, can you expand? Thank you, Harald. As always, very stimulating. Can you expand a bit on what you mean by open-ended in that last sentence?
Yeah. Like the PCA and PLSR, a neural net has the ability to model both things that you expect to find and things that you didn't expect to find. I'm not an expert on neural net, but at least I can say that the PCA and PLS regression is something you start out with a minimalistic model, where you start out, what we say, I know nothing. And then I know a little bit, but now a little bit more, and now a little bit more, and then you said, no, now it stopped, because now the predictability, the error goes back up. So open-ended means that we are combining the modeling of the knowns, and we are open to that there is also some unknowns. And the nature of those unknowns is that they are systematic patterns. And so we have an open-minded and open-ended modeling of how many patterns need to be modeled in order to get a good predicting ability. That's what I mean. So there was a famous book 20 years ago, The Closing of the American Mind. I'm not saying that Americans are worse than us, but I'm just saying that the closing of the mechanistic mind is one thing, but then I sometimes feel that this is machine learning. It's so open-ended that you start out with something like this big, 500,000 parameters, and then it's like an anthill with 500,000 ants. And then explainable AI people, poor people, come with a stick or a hypothesis and stick into the anthill and pull out and see, and then taste and see if they have found something that correlates inside the neural net. And the informative converse says that you shouldn't taste that because there are some ants sitting on that stick and they will bite you in the tongue because you are not only getting out what you were looking for, you are getting out something else too, and you don't know what that is. So this is philosophy of science, deep philosophy of science.
One more question before I go to coffee break. I have a question.
Okay.
So the interesting thing one of the interesting things that you showed is that we should look a little bit closer into the low dimensional manifolds that we create upon the transformation degree, right?
Yeah.
That would be something interesting to do. I know that some mathematicians that are working in algebra related machine learning, like studying leaf groups and stuff like that using neural nets, their aim is to look into the low dimensional manifolds, low dimensional but still high dimensional, and the properties of the manifold of the compressed representation done by the neural networks. Maybe we can look at there for causality mechanisms that try to help us, just instead of looking into the results, that the prediction, we should look into the low level representation of the manifold that the neural net creates.
Yep,
Maybe
that's
we have some
the neutral parameter is called neutral parameter set. When you then do multivariate analysis of that, you can see the structure of doubt. Very important, not to only to say statistically that we have these variance and these covariance. You should open up the space or subspace of doubt and look into the structure of doubt. I have to just show that if you have spectra, and there are some things that you understand and something you don't understand. If you forget that, and you have your spectra and you think you know the spectra of your analytes, what happens is that the only thing you can get right are the concentrations of the unexpected. You don't get, you get the wrong estimates of your analytes because of these interferences. You get the wrong estimate of the spectra of the interferences, but you get the right concentration of your unknowns. Bizarre. Likewise, if you know, like in statistics, the analysis of variance, if you know the concentrations and you have the NIR spectra, you cannot estimate the right spectrum when there is something unexpected there. You cannot either get the concentrations of the unknown, but you get the spectra of the unknowns. It's like Bob and Alice. It's like Heisenberg's uncertainty principle. It's a duality. You can either have one row vector and one score vector here, or one score vector and one vector here. Right. The rest will be wrong. It's puzzling. Linear algebra.
Okay, let's think.